Apparently I have 3 webcams going. So let's get started. Tell me if you hear the echo. Does everyone hear the echo today that we heard yesterday? I think the problem was I had the same audio equipment coming in on like 2 different sources, if that makes sense. So there was like a layering effect. Is it okay today? Great. Okay, that's good. So today we've got these 2 lectures to go through. One is like system modeling, which is like a core design lecture, and the second one is like a Git thing on unscrewing history. And these 2 things are actually pretty short. I was hoping to cover 8.2 as well, but the problem with 8.2 is that I can't log into my slides website today for some reason. It's giving me like, oh, you all get this now because you're working with web servers. I try and log in with Google and I get this response and it says something may have gone wrong. It said it before somewhere, but it's like, this is like a 500 error, right? So we're having an actual problem with the servers crashing. This isn't like the front end's problem. But we'll get back to that. So first thing first today is system modeling. So this is a topic in the SDLC design area, which basically means like this is the step after you kind of figure out, you know, the requirements you're working towards, but you've yet to code something. We need to make sure we're designing it properly, right? And design is that process again where you sit down and you think, before I code, what's a good way to approach this code? You know, the most basic example of this that they give you when you're, you know, doing some first year courses is like pseudocode, where you sit down and you try and write your code out in plain English or something first, and then you go away and actually write it. So, yes. System modeling, though, is a really fancy word to just simply describe, before you build a system, you actually sit down and you kind of map it out, right? Think of it like a little bit like a mind map for a software project is kind of the simplest way to do it. And you could have done this for your project if you wanted to. You could have sat down and been like, okay, we've got all these different data types and draw it out and everything else like that. There's lots of different approaches to that. Today we're going to talk about a couple of things, but first thing, system modeling. It's like, what is a model, right? And you'll hear like the word model thrown around a lot. And, you know, when we talk about modeling computer science, obviously we're not talking about those people that get dressed up and walk around on stage. What we're talking about is this ship, this model ship. This is one of the 3 or 4 slide decks in the course that another lecturer wrote, so I get surprised by the things that are in here sometimes. But we have this model ship, which is basically, you know, we're trying to make a bigger ship except on a tinier scale. And it's like, why would you do that? Well, you do that to represent something. And there's lots of representations you're familiar with, even if you haven't worked with them before, right? Like whether it's trying to represent the atomic model or draw a flow chart of a system, or other types of flow charts of systems. Things you draw on the back of paper to try and make sense of what you're doing. A lot of math is basically models, right? Like you think about all those big equations you've seen, you know, equals MC squared and all these things. They're all models of the universe, right, in a way. And yeah, like models are things you're familiar with. They're ways of representing stuff. So a conceptual model, though, is a particular type of model, right? Like you kind of get models like model aeroplanes, model ships, like the very first example we saw. But a conceptual model is something slightly different. And a model that's conceptual is something that has a real-world correspondence, but it's like, how would you put it? It's like a conceptual model of something real, right? And a good example of that's diagrams. Like you see these kinds of diagrams. So this first one here, this model ship, that's not a conceptual model, whereas these other things are here. Because they're trying to describe real world things in like non-real world ways, right? Like non-physical ways, basically. So models represent things. Conceptual models are abstract ways of representing things. And as software engineers, or really any kind of engineer, we use conceptual models a lot for a ton of things, right? We use them for like data models, right? Again, like drawing a diagram to represent data. Mathematical models, you've all worked with that whether you realize it or not. Data flow models, they're like use cases, right? Like a use case diagram is a model of sorts. You could argue it's a conceptual model. they're just ways of representing things. So you don't have to like think this is some big topic. It's really just a way of formalizing that, you know what, in the world of software engineering, we actually really care about drawing things to try and represent the world around us. And the main reason we do this is for communication, right? Like we want to be able to communicate things effectively. Because if we can't communicate things effectively, then, you know, we're screwed. So, because no one will understand what we're doing. There's another type of model, though, which is state transitions. And these are the ones we're going to talk about today. So, how are models used? Like, why do we use them? Why do we draw things like use case diagrams? Why do we have things like mathematical models? I mentioned that they're representations of the real world. In reality, we use them to predict future state of affairs. We use them to understand the current state of affairs, to be able to make sense of the past, right? You've probably all heard about like climate models, for instance, where, you know, people have these big mathematical equations and other things that help them look at, you know, what's going to happen in the future when it comes to sea level rise and temperature changes, right? And often models are simplified. You're not trying to represent the entire system. Like, you're not trying to represent every single part of it. You're just trying to represent like a simplified and fundamental version of it. And this is true for most models, right? Like even a diagram by its very nature is a simplification. So we're not trying to go over the top with it. When it comes to communicating these things, there are kind of a couple of key things that you like always want to consider when, like, say you're drawing a diagram. Like whenever we say like a model, think of it like a diagram for now. And as I mentioned before, it's all about communication, right? Like that's why these things exist. So you're trying to often convey information to stakeholders, right? Because people who are making models are like, you think of again about like climate graphs and all that kind of stuff. Who's writing these graphs and who's making these models? Well, they're people who are trying to communicate it often to government. And then you look at things like, you know, they need points of reference for system designers. So it's like what does provide a point of reference for system designers to extract system specifications? Well, again, it's like if you have a use case diagram now as a software engineer, that allows you to be like, oh, I see the key parts of this. Now I can think about building an API better, for instance. So, you know, if you start off with requirements that then turn into things like use case models, like the ones we did yesterday, then suddenly as an engineer, you can be like, oh, I can see how this fits together more, and I can see like the key behaviors and actions that take place. And it's also a form of documentation, because when people come along down the line, new people come on or the project's handed off to someone, they can see how you've been thinking about it. They can see how you've designed it. Because a system that's well designed and that design is well documented will fundamentally not need a ton of like digging into the code, because you're like, okay, I get what this does. And you don't have to try and make sense of things via code, which is the worst way to make sense of things. Now, within conceptual modeling, a lot of the modeling we've been talking about is what we would call system modeling. Sorry, just lost the page. Where'd you all go? There you are. Yeah, it's called system modeling. So think of system modeling as a type of conceptual modeling that focuses on systems, right? Because you could conceptual model performance or user behavior or something. Like you could conceptually model virtually anything, but system modeling is saying, okay, we've got this software system out there. How do we actually describe that system? And the main way that they come into effect is either through like there's a few terms you haven't heard before, but like a couple ones are like, you know, UML diagrams, entity relation diagrams, which are basically ways of trying to explain to someone, this is the entire software system, and they explain it from a different lens, right? Like a UML diagram, which you do in other courses at uni, is trying to focus on, these are the key software components, kind of like files nearly, and things like ER diagrams are trying to say, here are the key types of data that we have that exist. So they're just different ways of emphasizing the structure of the system. You know, maybe a data-focused one, maybe a structurally focused one for like all the code you have. And then we have the other type of model, system model, which is behavior models. And these are ones you're kind of used to because we covered them yesterday, which is rather than taking like a static view of the system, right? Because all of these other system models are these structural ones are static, as in it's just like a snapshot, and that's always the software system, irrespective of how it's used. This is just what it is. A behavioral system model is something that actually says, all right, well, how are users going to use this? Okay, they're going to start here and go here and go here and go here. So that's what a use case diagram is, because it's describing behavior of people. And then a state diagram, which is next, is a state diagram that's next is something that tries to describe like what's the state of the system as a user moves through it, right? And this is something that you kind of can't really do in courses like COMP1531, because all of your applications are what we call stateless, in terms of like you just like run them and they finish a lot of the time. Whereas if you think about something like the UNSW Dreams project, you know what it's like the system exists and then it has users and then maybe it has messages, and you could model a user going through the system. The reason this topic matters is because you will be how would you put it? What you'll be doing in iteration 3, which we'll talk about next week, is you will actually be, what would I say? Like, you'll be trying to do some system modeling on a future feature that you've yet to write, which we will be expecting you to write a state-based model. So this is where we get into state machines. So state machines are a type of behavioral system modeling. So these are all conceptual models because it's not something physical. These are system models because they're describing the system, and then of the system models, this is a type of behavioral model. And yes, so what is a system model? Well, when you often look at machines, right, machines are made up of a series of states. And like, what's a good example about this? Well, even think again about like that ATM example that we talked about yesterday, right? Where, where, you know, an ATM, you like come in and you enter the PIN and then it gives you the cash and it gives you these options and stuff. It's like, you can actually imagine these ATMs as state machines, right? Because they're essentially moving between different types of states. Now, when you try and transition from one state to another, that's just what we call a state transition. So like a state machine diagram is basically just made up of states and state transitions. And in this case, like, this is an example for a door. Like, if you're working with a door, then the door is either open or closed, and you can move from a closed state to an open state, or you can move from an open state to a closed state. And this is quite intuitive, right? It makes sense. You just move in that direction. While there's no like strict notation to this, like it doesn't have to be circles, it doesn't have to be arrows. I mean, you need some way to denote direction. Like, it doesn't have to be perfect. The general gist is quite obvious. You have blocks, and then you have connections between blocks that are directional in nature. And those connections typically describe the transitions. You can write more interesting state machine diagrams though, particularly for like modeling systems that are quite big and have clearly defined states, right? So, you know, maybe something like your UNSW Dreams app, maybe something like your computer at home, you know, like you turn it on and then it boots up and then you log in and then you like do something and you log out, right? You're moving between these states. And like, if you're struggling to visualize this, then it's like, here's a state machine for a parking meter. You know, these are the ones you go up and you insert coins in them to get tickets. And like with a parking meter, for instance, you you know, you come up to a parking meter and its initial state is in like an enter parking bay state, right? Where it's just like, hey, I'm here, enter the parking bay. And then you look at all these lines, right? There's 4 lines in and 1 line out. So the only thing you can do from this to transition to another state is enter a number input. And when you enter that number input, it says enter your duration that you want to park for. Okay, so now you enter another number input, right, to insert some coins. And that's the only thing you can do from there. Sorry, I lie. So like from enter duration, if you don't want to input your duration, you can obviously cancel it, right? So you enter your car spot number, then it says enter how long you want. You either cancel it or you enter how long you want. And then after you enter how long you want, it's going to tell you the price. It's going to say insert coins. It's going to you can either insert those coins continuously until you put in enough, or you can cancel and the coins are ejected. And if you put in enough coins, it'll say sufficient funds. Confirm. Right? And then from confirm, either like you can click cancel to eject the coins, or you can click OK and you get taken back to the start. And they're like quite straightforward diagrams. They don't really need like a ton of explanation. But they're really useful. Like if you were to give a software engineer or a hardware engineer and say, I need you to build me a parking meter, this diagram is going to speak more clarity than pretty much any form of written communication that you have. So that's why they're very powerful, and particularly for state-based systems. And in reality, most systems that you'll work with in your life will be state-based. Yeah. And you could do this exact same thing for like an Opal Card system, right, as a state machine. Like you think about like a Sydney transport thing where you have like an Opal Card, right? And like, what's your Opal Card? It's in like an uninitialized state. And then you tap on somewhere at a station and it's in like a tapped on state. And then if you tap on at another station, it's in like a tapped off state awaiting transfer or something. So, and then after an hour, it like goes to an uninitialized state. And if you tap on again in that hour, then you're in like a transfer state. You know what I mean? Like, because the Opal rules are quite complicated. And after 5 hours, your journey gets cut and stuff like this. So you can model things like Opal Card systems as state machines. It's quite straightforward. But I mean, I do think that this topic is largely putting a name on something that many of you kind of understand. So I guess my main question to you is just going to be, do you have any questions about this stuff, or is it pretty self-explanatory? I don't think everyone does the like 2141 though. So yeah, that's okay. All right, well, that sounds good. Great. Well, that's pretty much all there is on state machines. So again, the way this comes up in your course, this course, is that you are basically going to have to do one of these as part of iteration 3 and maybe interpret one on your exam. That's the main thing. So if you just feel comfortable enough with it that you could draw one in a project, and you feel like you can interpret one as part of an exam, then that's really all there is. Like, in an exam we might say, a user goes to enter a duration in a parking meter. What are the next actions that they can take, or something like this. So it should be pretty straightforward. Yeah, that's pretty much it on state machines.